My name is Jonathan Mugen. I'm co-founder of Deep Grammar, and what we do is we correct text when you write it. So growing up, I always made a ton of mistakes when I wrote. I still do that now that I'm an adult, and so Deep Grammar helps correct those things. We use deep learning to do these grammar corrections. I'm not going to talk about deep grammar today. Today I'm going to talk about going from natural language processing to artificial intelligence. So, it is not my aim to surprise or shock you, but the simplest way I can summarize is to say that there are now machines in the world that can think, learn, and create. Moreover, their ability to do these things is going to rapidly increase until in the visible future, the range of problems that they can tackle will be coextensive with the ones that we can tackle. So that was Herbert Simon in 1957. And so here's where we are in 2016. You need to start understanding me, Siri. I'll make a note of that. Yeah, you better make a note of that. Got it. Of that. So I talked to Reza today, and he said that they actually have fixed this since he posted this on Twitter, but we still have these kinds of problems. And so what's going on here? There's no actual understanding. So AI has gotten smarter, especially with deep learning, but it's still all very superficial. Computers can't read or converse intelligently. So to understand language, computers need to understand our world. They need to be able to answer questions like, why can you pull a box with a string but not push it? Why is it unusual that a gymnast was able to compete with one leg? Why does it only rain outside? If a book is on a table and you push the table, what happens? And if Bob went to the junkyard, is he at the airport? These are all very trivial things that a child who hasn't even started preschool yet generally knows, but our computers don't. And the reason there's such a big gulf is because we understand language through a representation that is grounded in both sensation and action in our world as we manipulate things and move through the world. And so when someone says chicken, it's not just a symbol, it's everything we can do with a chicken. It's all the memories we've had seeing chicken and buying chickens. And we can understand each other because we've all had these similar experiences with chickens. And so that's where the understanding comes from, and that is what computers lack. So today I'm going to talk about two paths that we could maybe move to this meaning. No one knows how to really get computers to understand meaning yet, but there's two paths that people are working on, and we're going to cover those. So the first is a symbolic path. So you start off with meaningless tokens. Then you move to building manual representations of symbols and relationships between symbols. Then you do world models, kind of like the ones Tenenbaum was talking about yesterday. And then you merge the representations and models together into a more grounded understanding. The second path is pretty popular right now. It's the deep learning, subsymbolic neural network path. So you have word-to-vec, sequence-to-sequence models, which is the machine translation stuff that Google's been doing and a lot of other people. Then it can move to question answering, and finally external world training, where the robot is grounded in understanding the world the way that we do by interacting with it. So we're going to first go down the symbolic path, and we'll start with meaningless tokens. So when I first got into natural language processing, I was really depressed to learn what we do. So we have this bag of words representation. So we treat words as arbitrary symbols and look at their frequencies. And so this means in a bag of words that man bites dog is the same as dog bites man. And so we start off with like a vocabulary of 50,000 words, and a sentence will be represented by a vector of length 50,000, where place 1 is aardvark, place 2 is 8, and maybe place 49,999 is zoo. And so the bag of words with these 50,000 dimensions might look like this. The aardvark ate the zoo, and so you have a 1 for aardvark, a 1 for 8, a bunch of stuff in the middle, and a 1 for zoo. So we can take it one step a little better, and we can count how many times aardvark shows up. If we do that, we get this thing called term frequency. And so now we have a new vector that's 2 for aardvark, and 1 for 8, and 1 for zoo. We can do even a little better than that because aardvark is a pretty weird word. It doesn't come up very often. So if a document talks about aardvarks, that's probably pretty significant, at least in terms of distinguishing it from other documents. So we do this, we give rare words a boost, and we multiply each word by a measure of how common it is in the corpus. This is the inverse document frequency. And so you take the log of the number of documents divided by the number of times that term shows up. And so if you have 10 documents and only one has aardvark, but 5 have zoo and 5 have 8, you want to give more. When you're representing a sentence with a vector, you want to give more emphasis to aardvark because that makes it more distinctive. And so we have this TF-IDF, term frequency inverse document frequency, the aardvark ate the aardvark by the zoo, and we have 4.6 for aardvark when you do all the math and everything. And so this is called the vector space model. And so we can throw these vectors into a classifier and maybe do sentiment analysis. If we have a bunch of positive movie reviews and a bunch of negative movie reviews, we can run a machine learning classifier on this. Or we can also take a document, put it into its TF-IDF form, and find similar documents. So this works pretty well, but there's no meaning and understanding going on here. It's just symbol matching. So another thing that's just raw symbols is LDA, latent Dirichlet allocation, and it's a good way to get a good sense of what's in your corpus. So LDA starts off, you pick some number of topics that you think are in there. So like 20 topics. You say, I bet there are 20 topics, and you can change that later and run it again. But you first have to say, okay, I bet there's 20 topics. And then what LDA does is for each of those topics, it learns a distribution over words for the topic. And then you can go look at those distributions for each topic and then kind of manually say, oh yeah, that's this other thing. And each document then becomes a distribution over a distribution over topics. So each document is a distribution over topics, and you can kind of get a vector to represent a document in that way. And so in Python, this is real easy to do. There's a Gensin library. You just go there and run it. And in fact, there's a beautiful way to visualize it called PyLDAViz, where I took my tweets and I threw them in there, and I looked at topic number 4, and it looks to be when I tweet about movies. So I have movie, watch, make, night. So this is a good way to get a good sense of what your topics are. I picked a number ahead of time, and the red is how often it shows up in that topic, and the blue is how often it shows up in just topics in general in the corpus. So that's LDA, and it's kind of fancy and neat, but we still don't have any meaning anywhere. So we get our first sense of meaning in sentiment analysis when we do it other than the way I just talked about. If we do it with the way we just supervised classification and TF-IDF, there's still no meaning. But we can get some meaning by creating a dictionary. So a sentiment dictionary. So we take all the words that in the English language are all the ones that might be indicative of sentiment, and we give them a score. Happy is positive, joyful is positive, pain is negative, painful is negative. And with the sentiment dictionary and some simple rules where we say no or not, it reverses the sentiment, so not terrible would be good, or at least not terrible. Then we can get a good sense of the sentiment. And this works pretty well for just kind of high-level sentiment, easy, quick, and easy. There's a library called Vader. These slides should be available on O'Reilly, so you shouldn't have to run any links down that you see. That kind of handles that, and it also handles the negation. So we've dealt with meaningless tokens, and now we want to talk about manual representations. So what we can do is we can start building up meaning manually by doing it by hand. So we tell the computer all the things we're going to say by building symbols and manually creating relationships between symbols. And that allows us to define what the computer should do for text if we can map the text to this representation. So imagine that you're a tire company and you're looking at Twitter and you want to find out who might be in the mood for some tires. Right? And so you'd set up a representation like this. You say, okay, a vehicle has tires, and a Honda Civic is a vehicle. Now, setting up this representation, of course, in its full glory is a lot of work, but this is kind of how it would work. And then when someone writes, you can say, cruising in my Civic. Every time somebody writes that, you go, Honda Civic is vehicle, tires. Boom. That guy needs tires. This guy says the car, an automobile, my truck. All those go to vehicle, vehicle has tires. And so one of the most famous manual representations is called WordNet. So WordNet organizes words into synsets, where each synset is like a set of words that correspond to one meaning. And a word can be in multiple sin sets. So let's see here. So we have the sin set for car has 3 words: auto, automobile, motor car. That box means car. Now a word can be in multiple sin sets like bank. So bank has multiple meanings. It can be a river bank or a bank where you deposit money. So you set up this sin set, and then, well, they do it in WordNet. So WordNet has a sin set, and then it has certain relationships between the words. So one is has part. So car has a horn, and that's the sin set for horn, which is all the words that mean horn. And it is in a superordinate relationship with vehicle, right? So car is a kind of vehicle. And then it has a subordinate relationship with sports car and ambulance. And there's some other relations with WordNet, has instance, has member. But that's basically what it is. It gives it meaning for words, and it's really popular and it's really useful. So FrameNet is taking it to the next level. So WordNet looks at the individual meaning of words, but FrameNet talks about situations. And so like a child's birthday party, they're kind of all the same, right? But there's a few things you have to change. There's a source of entertainment, and there's usually a location, and then there's a source of sugar, whether it's cake or cupcakes or whatever. And then with those 3 things, you can create all kinds of different birthday parties. Another one is commerce buy. So that's a frame when someone buys something from someone else. And so with commerce buy, you have a set of roles associated with it. So this frame gets triggered by certain keywords. So if Bob purchased something from Tom, so then there's roles. There's the buyer, which is Bob, and then there's Tom, which is the seller, and the thing being purchased might be whatever's being purchased. So if Bob purchased a car from Tom, then the thing being bought is the car. And so we have a symbol now, or like a linking of symbols that represents this situation in a machine-readable form with some amount of semantic understanding. So there's some semantic understanding, but the car actually went from one person to another, and we don't quite have that in the frame. I mean, you could build that, but it's not built into this representation. So there's this thing called ConceptNet, which is like FrameNet, but it's actually a little closer to WordNet, but it's for common sense world knowledge. So you have bread is located near a toaster. Well, that's good to know. But it also says that a toaster is related to an automobile. And that's true, but you can't possibly write down all the things that are related in such a tangential way. This is a fool's errand. So, it could be useful in certain ways. Let's say you have a bot, and anytime anyone brings up toaster, you look for something to say about it, and you say, what's by a toaster? Bread. But it's hard to say what other kinds of things you could do. Yago was used in part by Jeopardy, used by Watson to play Jeopardy, and Yago is an ontology built on WordNet and DBpedia. So DBpedia is real useful. For every Wikipedia page, there is a machine-readable form in DBpedia. It's got its doppelganger in DBpedia. And so Yago kind of ties these together, and then you can browse Yago. And what this means is Yago is really good for named entities and entertainers and sports, the popular culture kind of stuff. It doesn't go deep, but if you need to know stuff about pop singers and that kind of thing, it's really useful. So I keep saying they don't go deep. What do I mean by these representations don't go deep? Well, Sumo is a manual representation that does go deep. So it organizes concepts down at the lowest level. For example, cooking is a type of making that is a type of intentional process, that is a type of process, that is a physical thing, that is an entity. So that goes all the way down. And that's nice because it's really well organized, and it's tied with WordNet to some degree, or I think pretty well, tied with WordNet, and I'd like to see this be used more. It's good stuff. And so there's also a Yago Sumo that kind of merges the high-level stuff of Sumo, the high-level stuff of Yago with the low-level stuff of Sumo that could be useful in some situations. So even below the Sumo, there's representations that are below language. There's representations that are common across languages. And these are things like containment. So water is contained in a jar. That means if you move the jar, the water goes with it. Support, the table supports a computer, which means the table keeps the computer from falling to the earth. These are fundamental things that we're either born with or we learn very quickly. And we need to build these in if we're going to have a complete picture. And to my knowledge, there's no convincing implementation of these kinds of image schemas, these kind of bottom-level things that we need to do to get full or closer to full understanding. And then we'll take a quick, just a quick thing at the semantic web. It's not, it could be really cool if it gets organized, and right now it's just really complicated, and I've spent a lot of hours trying to understand it, and I've gone through, and it has been useful in certain cases. But if we can get it all tied together into the representation and get it flexible, it could be really cool in the future. So something to keep an eye on. So we've gone to meaningless tokens to creating manual representations. But we just have representations. We don't have anything about the dynamics of the world. So some of you might remember Josh Tenenbaum's talk yesterday about models of the world. So our agents need models of the world. And so a model, particularly causal models, if I do this, this happens, is really useful because when we talk, we don't say everything that needs to happen. So the joke I like to say is imagine a romance novel where the couple looks at each other across the table and they look into her eyes and then they push the table aside. And in the romance novel, they would never say, as they pushed the table, all of the objects on the table moved because they were supported by the table. It just wouldn't be in there. And if you're going to learn from text, you're never going to learn that because we only say what can't be implied or understood from our low-level causal models. And so models express how exactly something happens. So I mentioned with the commerce buy frame, we can identify, hey, commerce buy, here's the buyer, here's the seller, here's the thing. But what's the state of the world after commerce buy is triggered? If you have a model, you can just read it right off the model. You're like, oh, okay, now Bob owns the car. You don't have to do any kind of complex inference. The model just hands that to you. And there's a lot of different ways to build models. So Josh Tenenbaum yesterday talked about probabilistic models. But these probabilistic models can factor the state or keep the state as one individual thing. They can be relational models between objects. They can be concurrent models, like finite automata compared to Petri nets. Or they can be temporal models, so a Bayesian network compared to a dynamic Bayesian network. There's a lot of work that is working in these individual areas and some crossover. We've got a lot more to do. So now we have the world models. And we want to take the world models with our manually created representations, and if we can have world models, detailed models of these representations, we might be getting close to something like intelligence. And we would know when we're getting close to intelligence when we can ask a computer a question like, okay, why does it only rain outside? And it says, well, the roof blocks the path of things from above. We're like, okay, that's pretty good. Or explain your conception of conductivity. And it says, well, I think of it in terms of electrons as small spheres and electricity as small spheres going through a tube. Conductivity is how little blockage is in the tube. This is from first principles. And of course, we could just write a computer program to generate this text. But the point is, if it could do it on the fly from first principles, then through the symbolic path, that would be some real intelligence, and that would be cool. Then it could actually talk to us and understand us and do the things we want to do. And so when we say the word chicken, it would use its experience with chicken or its deep models with chicken to understand that chicken is not token number 48. Chicken is everything we can do with chicken. Chicken is what happens when you go to the store and you pick it up and you put it in the bag. Chicken is all these things. Now, there has been a project called the Psych Project that's been trying to do this with logic for a long time. I don't know how well it works. I really have a hard time finding out about them, but my suspicion is that logic is not sufficiently supple to handle all this. So that's the path of symbolic path. So next I'll talk about the sub-symbolic path, the deep learning stuff that we've all been so excited about in the last few years. So a great way to get started is maybe not a great way, but a cool way to get started is one of the original papers, Parallel Distributed Processing, Volumes 1 and 2. It's surprisingly readable, really good stuff, and you feel like you're at the real source. Of course, they've been working on these things way back before that, but that was a nice synthesis, and a lot of modern ideas came out of these volumes. So word2vec. So word2vec model learns a vector for each word in the vocabulary. I imagine we've probably all seen this by now. Compared to TF-IDF, which is like 50,000, if that's the dimension of your vocabulary, word2vec is usually like around 300. And instead of being sparse, it's dense. So every index has a value, and it's also a distributed representation. It's hard to go to index number 48 and tell what that means. It doesn't mean aardvark. Who knows what it means? So here's the algorithm for word2vec, and I first saw this explanation from Christopher Moody. So you initialize all your words with a random vector, all the words in your vocabulary, and then you just loop through. So let's say you have 50 documents, and you loop through the first document word by word, and for each word, you take the vector for that word and the vectors for all the words around it, say 5 on each side, and you move them all a little closer together. You make them a little more similar. And then for all other vectors that aren't that word and not in the window, you move them a little further apart. And that's it. You basically just keep doing that over and over and over again. That's word2vec. So the quote we often see with word2vec is you know a word by the company it keeps. And this seems kind of true. So these vectors have been shown to have internal structures. So if you take the vector for Italy minus the vector for Rome, you get something pretty close to the vector for France minus the vector for Paris. In fact, when people create these algorithms for learning vectors for words, they use analogy tests like we took in high school to evaluate how well the word2vec is working. But as we saw or talked about earlier, most experience is not in the words. We only say what can't be easily inferred. So you can't actually learn a grounded understanding of the world based on reading text. You can do some cool stuff, and the best thing about word2vec is the similarities. So if I talk about a Toyota and a Honda, it may learn that the vector for a Toyota and Honda are pretty similar, and it'll treat them the same. But in the symbolic method, I actually have to manually say, okay, a Toyota is the same thing as a Honda. Or I have to manually say a Toyota and a Honda are both vehicles. So this word2vec can learn these kind of similarities very well, and that's very useful. So then the next path is what's called sequence, or next step is what's called sequence-to-sequence models. So these first came out of the machine translation, was their first real hit record for sequence-to-sequence. And so it encodes tokens using a recurrent neural network. So you take all your English text, and you have this huge thing of English text, and for each English sentence, you have the Spanish translation. And you encode the English in a recurrent neural network, and then decode it into Spanish. And we'll see how that works. So machine translation is an obvious example, and we'll go through that. So the patient fell, right? So you take like the word vector for the, can initially be a random thing, it can be from word2vec, and you find, you make that your initial state. Then you take the next word, patient. And so there's a recurrent neural network right here that combines the previous state vector and the new word vector into a new state. And that recurrent neural network in its very simplest form is two matrices. The first matrix multiplies by the incoming previous state vector. The next matrix multiplies by the word vector, and you add them together and put a nonlinearity on the end, and you get a new state. And you just keep doing this over and over again, all the way to the end. You create H2 from the previous state and fell until you get to the end. And then you have H3, and now H3 is a vector, the same length as the other vectors, 300 or whatever length you like, and it represents this sentence, the patient fell. So now we're going to train it to translate this into Spanish. It's like a hidden Markov model without the Markov assumption and the vector representation. So for machine translation, we start off with the previous state, the state we ended with, and we generate a word. Then we're doing a decoder now. We're doing a new RNN where we have in the simplest form, a matrix that multiplies by this, plus a matrix that multiplies by this with a nonlinearity on it to get this new state. And you've probably heard LSTMs. LSTMs are a more complicated form than I just described here to generate this new state. They actually have a couple states in their state, but they're just more complicated so you can remember things longer. But the basic idea is the same. So now we have a new state. So what are we going to do in our new state? We're going to generate another word. And so we generate that next word, paciente, and now we just keep going like we did before. Now remember, every time it generates a word, it gets some cost. Because what if it generated the wrong word, or even if it generated the right word, there's a cost. And that cost gets propagated all the way back into the encoder, all the way back into the vectors for the words in the encoder and in the decoder. And that's why you need so many training words, tens of thousands, hundreds of thousands. You need all that because you're training millions of parameters. These vectors these matrices that you multiply are very huge. And so you just keep going. El paciente cayó. Now, if you speak Spanish, you know there's an error here. It should be el paciente se cayó. So this translation doesn't have to be the same length. It just keeps going, generating tokens until it generates a special stop token. Okay? And so this is devoid of meaning. It doesn't know anything about this. It's just taking tokens because the first step you do when you're doing this is you take each word and you map it to an index, like an integer between 0 and 50,000. And then the training data actually looks like lines of numbers. So there's no meaning here. And in some sense, that's good because it means it can work on many different kinds of problems. And we'll see another example in a second. But in another sense, it's bad. It feels like translation should understand what it's translating. So what we could do here, and I mentioned another example, another use case. So we have a child here, a wet child, and we can take a convolutional neural network and run it and get some vector that represents the child. And what we can do then is create a description. As long as we have a lot of photos that are captioned with a description, we have our vector here, and we just do the same decoder that we did before. And we just get our H0 as our initial state from the convolutional neural network, and we can generate sad, wet kid. So you may be wondering, well, as you're going, oh, and that's a mistake, there should be H6. As you're going further and further, generating, encoding more and more information in the same fixed length vector. There are always 300. So it seems like you should be running out of room in the vector. And so to partially get around this problem, they came up with something called attention. And so what attention is when you're here generating cayó, you don't just look at the previous state and the previous word generated. You can also look at the encodings of all of the sentence that you're translating from. So you're looking at a lot more information, and then you encode that in, and then you can make a much more informed decision when you're generating the next word. So that is word to vec and sequence to sequence. Now, what we saw at the end of sequence to sequence was attention, where you take that attention when you're trying to generate the next word, and you're looking over some set of previous data. So that's going to be helpful in question answering, right? So RNNs, in a sense, for current neural networks, in a sense, answer questions like, what is the translation of this phrase to French? What is the next word? And as it answers a question, it looks at all the facts that it knows, H0, H1, H2, H3. It looks at those facts and sees if they're relevant, and if they are, it uses them. So this could be generalized to a general question answering learner, and that's exactly what they've done. So they generate a whole bunch of stories of this form. So Bob went home, Tim went to the junkyard, Bob picked up a jar, Bob went to town. Where's the jar? Well, the answer is town, because once you pick up a jar, of course, you never put it down. So the answer is jar. And so if you train it on a bunch of stories similar to this, it can learn the answer correctly, which is really cool. But there needs to be so many stories that they have to be generated by a machine to create enough training data. And so this uses the same idea. Another example is navigation. So the office is north of the yard. The bath is north of the office. The yard is west of the kitchen. How do you go from the office to the kitchen In this case, with an RNN, it needs to generate a sequence of instructions, and pretty amazingly, it can learn to do this with just stories, but it needs a whole bunch of stories. And it starts from a tabula rasa. It doesn't know anything to begin with. And that's kind of depressing, because it feels like there should be some underlying principles that would make this easy. It feels like you shouldn't need 100 million parameters to do this. So the network is learning linkages between sequences of symbols. But these stories are not sufficiently grounded in the real world. You don't have to have real world knowledge to answer these. And we've seen some people talk about some work where they're using more world knowledge in this conference, and I need to follow up on that. My suspicion is that we still have a long way to go. So once you answer questions, the problem is these stories are generated about things that aren't in our world. They're kind of made-up stories. So we need external world training. And we have some of that. So if we want to talk to machines, it needs to be like our own. And that way we can understand chicken because it understands our own. Because it understands it the way we do because it's had experience with chicken. It needs some kind of real-world training. And it can be simulated, I think. As long as the kinds of things that move in the environment and act in the environment are similar to our real world. So in industry, OpenAI has some cool stuff where you can plug into video games. And of course, video games aren't like our world, especially the old Atari games. But as video games get more and more realistic, they'll be better and better for training. DeepMind's doing some cool stuff with learning in 3D simulated worlds, learning stuff like which block is the nice blue one next to the tall red one, and it can kind of use relationships to identify. And Facebook has been working in this a little bit as well. And in academia, there's some work, particularly the iCub, which is a robot out of Europe. And I think they've made a handful of them. And this, learning from first principles. You pick up a cup, you knock it over. This could be real learning. I don't know if we have to go this far. Imagine if Amazon Alexa had a camera and a rotating head, and she was with you your whole life. Could she learn, when your child is born, could she learn as your child learns? Is it even possible? Or would we need to explicitly teach it? Do we need to have, look, Alexa, that's a dolly? I don't know. Eye gaze is really important. So maybe Alexa could just, when it's watching your conversations, it could look at where you're looking and could help pick up on the meanings of words that way. And it's not clear if robots really need to manipulate objects to learn. That's an open question. It'd be nice if we could do it all in simulation or some kind of shortcut. I don't know. So this is the subsymbolic path. Now, on neither the symbolic or the subsymbolic path are we there yet. On both paths, we have a long way to go. But I hope in this talk that you started to get a sense of what the current state of the art is and what we still need to accomplish. So the symbolic path is building world models based on large, deep, and organized representations. The subsymbolic path is training neural networks in an environment with similar objects, relationships, and dynamics as our own. And so one problem we've had is why aren't we doing more of this bottom-up learning? And a lot of people say, well, the AI community doesn't realize the value. I think they do. It's just hard. We don't know what to do. And also, it's hard to get your foothold on it, and it's hard to get meaningful progress in a short enough amount of time that somebody will care, especially outside of academia. So the question that I'm interested in is, what is the simplest commercially viable task that requires common sense knowledge and reasoning? If we can come up with that, and then maybe we can build it, we can get some funding and do some cool stuff. Thanks for listening. I'll take questions. Yes?
What is your personal sense in terms of which path is more promising, or how do you think is the most promising?
Yeah, I actually don't know. The last year or so, I've been more symbolic in my thinking. The one problem with the sub-symbolic deep learning is that it has a hard time making fine distinctions. Like if you translate a sentence into I went to the store, or let's say I went to the store on 6th Avenue, and translate a sentence and I went to the store on 8th Avenue, those translations at a vector form seem pretty close, but they could mean a lot of difference, because if you're meeting somebody at one place and not the other, vectors have a hard time with that, where symbols do well. And surprisingly, there hasn't been a ton of crossover work, and I don't think it's because people haven't thought to try. It's just not clear on how to do that yet. So I actually don't have a good answer to that question. The sub-symbolic certainly has a lot of momentum right now. Yes? Yes? Yeah, so what we do with deep grammar is we use deep learning to check text. So what we do is we encode the text, we train on a whole bunch of unlabeled data. And then that gives us a sense of what good text should look like. Then we encode the text, and then we see when we decode it, we use like an encoder-decoder model. We use a whole bunch of neural network stuff, CNNs and the whole deal. But one big part of it is the encoder-decoder model, kind of like the machine translation. And what we look for is what you wrote unlikely, but close to something that is likely. So if you wrote, I went to the stored, so I went to the stored is unlikely. That last word doesn't seem to fit there. But store does. And store, not only does it fit there, it's close to stored. So that's a good correction. So we not only find where there's an error, we give you a suggested correction. And you can try it at deepgrammar.com. There's a place you can try out a demo. It just does one sentence at a time right now. We just put a single, we just got a real cheap server, a single one on Amazon. So, cool. Yes?
So, I know this may be a stupid question, but in gaming, they have models for world concepts, things like gravity and friction and velocity, and how those other things affect it. Or they have, not for objects as much, they'll have things like how aggressive or meek is a player, right? So the way that those things are applied to other objects in a scene, could that same approach apply?
I think so. In fact, I'm really excited about that approach. I wrote a blog post a couple months ago about maybe a computer could understand language by simulating it in a video game. So if I say, I walked home, what the computer does is it creates a little box for home at an arbitrary location, and it creates a little token for me, and just goes, dook, 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 and then puts me in the box. And then if you ask later, were you ever halfway between your starting point and the box, which is home, it's trivial to answer, because it just looks at the simulation and sees what happened. And these kinds of questions are really hard for inference-based engines to understand, because you have to put in all the inference rules, where the simulation, up to your detailed simulation, it all comes for free, because you can just look. If you say, hey, computer, what happens if I knocked a table? It's kind of similar to what Josh Tenenbaum was doing yesterday, but a little more in terms of just in general what happens. What happens if I knock a table? Well, the computer says, I don't know, and it puts some stuff on the table and knocks the table and says, oh, everything moves. Whereas you would never think to write that down otherwise. So I'm really excited. It would take a ton of work, because you'd have to build like, well, what's a house? Okay, we'll make it like a box. Well, but is it always just a box? Maybe sometimes it needs a window. Maybe you need a window, because you could go have a story where a guy went through a window. So you'd have to set up all this stuff. And it's very similar to what Psych had to do when they started, 20, 30 years ago, with building everything in logic. You'd have to do that again, but this time you'd build it as things that could be simulated. And I think it would be a lot richer than logic, and it could be really cool. Any other questions? Well, thank you very much for coming here.